Hello class, weekly update 4. Okay, lots of things grading this time. So you had several things. First, the optional survey, thanks to Maximus, David, and Asher for some suggestions on typos, edits, and survey suggestions. And I also, Madeline found a few this week as well. Okay, activities. Let's talk about some shout outs, and then I want to pull up a few examples, I think, here. So as usual, I dumped these examples of good work in the week 2 of this module 2 samples and examples. So for the finger twister activity, I really liked what Sharika did, and Calvin had a really nice explanation. For the f of x, f of y, du, those different types of derivatives, the explanations were really nice by Todd, Haley, and Noah. The cereal bowl activity, James, Isabella, Phoebe, Grace, and Aaron did a really nice job. Some nice images. I put those in there. I think we'll look at one of those as well. And then Madeline had some excellent explanations, and we'll take a look at hers. All right, so let's go ahead. Oh, and then in the calculations, just a few quick summaries. Haley, Sharika, Calvin did really nice work, doing almost all the problems. Noah had some nice step-by-step solutions, same with James. Madeline's was really nice again, and Asher did all the work as well. Okay, so let's go ahead. Those are shout outs. Let's go ahead and look at a few of these. Share the screen. Go to your Oaks page. Okay, so here we are. Module 2, samples and examples, week 2. So in week 2, again, here's those names again. I showed out Calvin, Noah, James, Asher, Phoebe, Gavin, Haley, and Asher again. Okay, and the one I want to take a look at first, I think, is Noah. His activities. Oh yes, so this is what, for the derivative matching, a lot of you just showed the matching and maybe a little bit of work, but this explains why he chose each one in his thought process, like it, whether it was running parallel with an X or Y axis. Same thing for the DU matching. So if you had trouble with those, or you, there's a few that still maybe don't quite understand the difference between f of x and du on the contour map. Take a look at what Noah's done. All right, then let's go back to the samples and examples and take a look at Isabella's activity. Okay, so this one I thought was a really nice visualization of the activity. Not all of you did this activity, so if you haven't, it might help to go ahead and look at what Isabella did. Let's move the page. Okay, so she's got her XY graph paper in the background, put the bowl over top, and then she cuts and showed this from several angles. The y equals b plane. She picks a point and draws the tangent line there. And this is exactly what f sub x, because you fix the y equals b plane. X is the one that's varying, and she just shows exactly what it is. So you want to have that visualization that when I get a number, when I compute f sub x at some point a b 1 1, I'm getting a number, and that number is the slope of a line that's in a fixed plane. Okay, then derivative matching. Again, a lot of people had just little notes here because which direction we're moving, and that was helpful as well. Okay, let's go back. One more I want to look at is Madeline's activities first. Okay, the finger twister, people, very similar, most people did a nice job just showing, yes, the tangent plane, and yeah, it should be tangent plane, is an approximation to the surface there. So you zoom in, it does a good job, but you're a bad job further away, but like right near the point, right? It's pretty close. And that makes sense because it's a smooth surface. Oh, I feel like some good ones for this to check out were, oh yeah, James, Phoebe, Grace, and Aaron also talked about the roof line. So they added like the roof line anywhere along that ridge line of the roof. You have, I feel like this is Shrika. Haley, someone had a really nice image that like, here's the tangent if I'm approaching the ridge line from this side, but then over here, if I'm approaching the ridge line from this side, this is the tangent. Since they have two different tangents, they don't match from which side I'm approaching it from, then I don't have a derivative there. So places where you have these sharp corners cannot be differentiable there. Everywhere else on your hand is nice and smooth if you zoom in close enough. Even like at a fingernail or something, right? You're just zooming in close enough, it really is smooth. You don't have these sharp angles. Okay, but here, here's what I liked and why I want to put Madeline's up here. Like she says, I'm really so confused by this. What's happening? You know, what is this 1/5, right? And then she works it out later on, but I just want to talk what this is too. This is just the same as 1/5 times the first component and 1/5 times the second component. So that would be 4/5 minus 3/5. That's the exact same vector. I just pulled it out. I should explain that next time, right? So that happened here as well. And those are your, I can go 4/5 in the X and negative 3/5 in the Y. So you would create a vector. At some point, I'm going a little bit in the X and a little bit in the negative Y. So it would be something pointing like that. She does some calculations. Yes. Right, so how am I going to match this? She eventually gets it. She works it all out. Okay, same thing here. Explaining her thought process for each one of these. And this is the one she said she had a little bit of trouble with at first, but shouldn't that be decreased? And then she understands what it meant in the choices that were below for the answers. Okay, so really nice explanation. And I liked, again, the thought process, and it's okay to see confused like this. That's also when you work it out, shoot an email to me. Madeline and I weren't able to collaborate on the time frame she had, but I think she got with Chloe or the math lab, or call your classmates, right? So there's other people that have thought about this very thing. Like, don't beat your head against the wall for something. I mean, there's value in that, and you eventually get it. But a lot of these could be just a quick thing. Like you tried, you thought about it for 20 minutes, go use your lifeline, find help. And plenty of those lifelines are people in class. And we encourage, keep saying that, please discuss these things with folks. Okay, the calculations, I want to take a look at Noah's. One thing that sometimes what I put in here, and all of you have done a really nice job in fact, this week I thought you did a really nice job in your calculations collectively as a class. But sometimes I just choose them for like ease of visually reading this and how organized. Some of you just cram it all in somewhere, beautifully done work, but it's just on a smaller page. And I like how Noah can separate them out. Shows very clear what he's doing each time and how he got these critical points. It works I think mostly all the problems here. Didn't have to do that many, it just does the extra practice. So please go in there and take a look at his, and let's go back to the next one. Asher. Okay, so we've got all, I think Asher did all of these again. Yes. Yeah, and he's going through showing his work and does a check. Yeah, each one. Sense of satisfaction with this. Okay, and we'll come back to this activity when we get to the next one. Okay, nice work. Take a look at your teammates, because again, did all 4 here. Last one is I have to pause every time I say Madeline, because I think Madeline, not Madeline. So I'm trying to do that right. Okay, so usual, again, calculations, we saw some nice ones, but just like last week, I think Madeline did this, she really wants to visualize and understand this. Well, we've learned these tech tools, so why not put them in there? And she goes ahead and puts the function, the tangent plane to see near that point. Is it really like an approximation? Doesn't do good over here, but right there. Okay, and then here's one that I really wanted to talk about this. Nobody else seemed to have comments on this. On page 178, there was an error, so thank you. I'm going to change this in future editions. All of you are like student editors. Anytime you see anything, things that confuse you is also helpful, so I can do a better job next semester. And so one thing that confused her was that, well, the answer is wrong, right? Let's say yes, no, and I put a true here, first thing, and then this is wrong. They should be no, no, the answers, and many of you just went through and said yes, yes, but you should have had a problem with that. You should have just been looking down there. And so she got to the right conclusion. Not all critical points are local extrema, just like in R2. They're good places to look, but what could they be? They could be something else. They could actually be what's called a saddle point, and you get to that in this chapter, right? You learn that keyword. And in this problem, or right here, actually is a saddle point, right? It looks like a min in this direction, but a max in that direction. You zoom in close enough, and it actually is flat and is horizontal tangent line right there at the center of that saddle. But that is not, that's a CP because it is horizontal tangent plane, but it is not a local extrema. And then the phrasing of this question, you're right, Madeline, is a little odd too. Local extrema don't have, so CPs, not all CPs are local extrema, all local extrema are CPs, right? Local extrema have to have horizontal tangent planes. So that was the summary, same summary that you had up here. Not all CPs are local extrema. All local extrema are CPs, right? Have to be horizontal. Okay, and then the other thing I think in Madeline's work was she talked about what does the phrase normalizing a vector mean? Oh yeah, okay. What else did she do? Yes, she talks about a first attempt and a second attempt on the problem, how we're going to get CPs, techniques for getting CPs. This also seems to be a place each semester that this is new. You're solving this system of equations, right? And that's something you haven't done before. And if you've done it, you've solved the system of linear equations. You haven't solved the system of nonlinear equations. There's some growing pains for that, some trial and error to try to figure out how you do this. And every CP problem is slightly different. You can't just have a methodical way of handling a CP because this f of x equals 0 equation and the f of y equals 0 equation, they're going to be different for each type of problem that you have. So you just need some strategies. And we'll see that, I think it's in the next module, I add some more practice with that. So I made another separate video just for doing more CPs and giving some more strategies. So don't worry if that is feeling like I'm kind of struggling and that's something that I'm not quite completely, don't worry, you'll get it because we're going to keep using CPs throughout chapter 3 again. You'll have more practice and I made more videos for you. Okay, so, but she does get it the second time around. But again, once again, she's like, let me check my work because I did all this. Are these actually CPs? What's a good way to check? Well, she goes and sees, does it have a horizontal tangent plane? And again, if you're having trouble with this view, remember use your, in CalPlot 3D, to use the keyboard arrow keys will help you like straighten that up and put the Z in the right direction. So if you're grabbing with the mouse and turning it, it's harder to control. Do it a little bit with the mouse and then fine tune it with the arrow keys. Oh yeah, so then she makes this point here. One of the things that confused her with the directional derivative was this idea of normalizing a vector and mean a unit vector. Normalizing, she's right, she gets the key concept. It just means taking a vector that's maybe this big, and I'm going to point it in the exact same direction, but I want it to be length 1, and right now maybe it's length 2, so I'm just going to shrink it and it'll be this big. And I do that by multiplying it by a scalar, right? Either dividing by 2, which is the same as multiplying by half. So when we say normalizing vector, we're just making sure it has unit length. Why we need a unit length is because all of our derivatives go 1 unit. You're either going 1 unit in the x if you're f sub x, or 1 unit in the y if you're f sub y, or 1 unit in any other direction if you're a du, right? But we want to keep that's to compare them, we want to keep that scale the same, so we make them all scale 1. Okay, that's it. There's someone else who had a really nice comment. I'm sorry for forgetting this, but one of you talked about how a directional derivative is kind of like a gradient, you know, because it kind of is, right? It's this weighted sum of a gradient. The gradient is the direction of steepest ascent. The negative gradient is the direction of steepest descent. And then the directional derivative is just, I'm not doing the steepest thing, but I'm just going in some other direction and I'm measuring how much I'm changing in z. So they're all related. Yeah. Okay, last thing to talk about now, because this is becoming a long video, is your challenges. So thank you for doing these again. I really enjoyed. Let's talk about every group, except for one, did the mountaintop number 3. And just a couple shout outs to group 2. This was Phoebe, Lauren, and Asher. They did all the levels 1 through 4. And, in that problem, so the only group that didn't do that was group 4, did the golf problem. And they actually had some problems with, there's a part of that where they asked about the direction of no change. And they're like, I can't find any literature on it. The only place in our book, and it's not in most books, is that challenge number 3 deals with the direction of no change. So we had talked about the gradient is the direction of steepest ascent. And if you look on a contour map, that gradient is always perpendicular to the level curves, right? So you could estimate the path of steepest ascent or descent by using the gradient and the level curves. You just always use that perpendicular property. But the direction of no change means you're not actually changing in elevation. And what you're doing is on that contour map, you have a level curve. You're going parallel to the level curve. And that means you're not rising or falling in elevation. You're actually staying at the same elevation. So we had this one where we were on a downward facing parabola, called that a mountaintop. We were at some ring there. That height, z equals k elevation, slices through this paraboloid, and we intersect and create a z equals k trace, which is a ring. At some point on the mountainside, the steepest ascent would be like that, the steepest ascent directly opposite that, but no change would mean just walk like this, and you'd be walking around the mountaintop. And that is, if this is our circular level curve, that is parallel right there at that point. Perpendicular is the direction of steepest ascent. So these directions of no change then are always parallel to the level curve. The gradients are always perpendicular to the level curve. That was sort of the key thing. But in level 4, it asked about why might you care about these directions of no change? And that group, Phoebe, Lauren, and Asher, came up with a couple neat applications that talked about base camps that you might want to be a place of no elevation. You want to be a nice flat area. They talked about maybe driving a top heavy vehicle where you don't want to have side to side sways as you're moving up and down around things. So you want to be very level. And then another group that had a nice answer, this was also group 9. This is Jake, Tripp, and Chris. They also did all level ups to this problem. And they had some neat ones. They talked about differently abled folks, where we were talking about accessibility to a building, right? If I'm in a wheelchair, I'd like to know places that aren't, are approximately level, right? I want these directions of no change. I don't want to be going to the steepest. I don't care about the gradient so much. I care about this direction of no change. So really nice job there. And then I want to do a screen share. The only group that did number 4. So challenge number 4 was about a golf. You could make your own 18th hole for the city's golf course. So it was very open-ended and creative. And it really ended up being a creative, fun way to make a study guide. And what was neat is that the nth dimension, that's the group of Madeline, Maximus, and Grant, chose to do this one. And the reason they chose actually was some teams choose by hey, I totally understand derivatives and directional derivatives, so I'm going to do challenge 3. Some groups chose challenge 3 because they didn't understand them and they thought it would help them clarify it, which it did. And that was the reason that the nth dimension chose to do challenge number 4. They were like, I don't think I understand some of these terms and it'll help me. I'll come back and they used it as a way to fill in gaps in their understanding, which is excellent. And I think that's where you want to start getting with this class is this is all for you to prepare you for your future majors, your future classes, and for our final exam, right? So you're just using this is time you have to spend to know this stuff by the final exam. Why not take advantage of that now and take the time to do it? And they made the comment that even though it took them longer than they thought challenge number 3 would have taken. It was time well spent. And so I just do want to share what they did. This is in my Google Drive, Google Doc. So I think that's this one here. Yeah, challenge. Group 3, we want to go challenge 1-2. Okay, again, this is the nth dimension, Madeline, Grant, and Maximus. Excellent job as usual, showing who did what. Teamwork was clear. They actually met in person. And it was clear that everyone's contributing and getting the most out of it and helping each other learn, like helping on the confused part. If someone was confused about pieces of the contour map, and someone else picked up the slack and was able to explain it, and they felt like they got much more out of it and had a deeper understanding by the end. So they're writing all these key terms, right? They're saying, what does this actually mean? And then they're going to put this on contour map for golf course that they've designed. This direction of no change was the one they had trouble with because they didn't do challenge 3, right? And that's the only place you would have learned it. So talk to any other classmates. They did that one, they could help you out. But I think I gave a quick little summary there. Okay, here's the final report. They all got together, used a whiteboard in the physics department, and came up with and they actually did several different designs before they got what they wanted. Beautiful drawings here, right? And they add a few features to the golf course. And then they start thinking about all the terms. Second, they tried another golf course design. I think this is the final one they had. Showing little errors, right? These are the way the ball breaks, but those are actually your steepest descents or negative gradients then. Yeah, putting in CPs, like this is a saddle point there, labeling everything on this graph with a legend. Yeah, and then their summary, like they felt like they totally understand, and I absolutely believe them that they will not forget this either. That's the thing. Like you've already done a great deal of studying for your final exam by doing this, because that's easy to recall. And students keep telling you semester after semester how shocked they are that like they sit down to study for this final that they were kind of getting a little anxious about, and because we hadn't had a little exam through the way, and like, but they find how much they recall, and it's easy. And like the studying goes much faster and easier than they thought. So start thinking about that this semester, like using these are all assignments that aren't meant to waste your time. They're meant to like prepare you, and hopefully they're fun as you're doing them, to prepare you. You can do them in a creative way. You can, they're open-ended, and there's many different ways to solve them, but they're all helping you study as you go on. All right, well, have a good time with the next chapter. So we're getting into chapter 3 with some really cool applications. Again, if you've learned how to take all these different derivatives now, like what else can you do with them, I guess. All right, we'll see you next week. Have fun.